But anyway, Elliot's grading them. I'm confident that we'll have those scores back next week sometime, hopefully early next week. And we'll take it from there. I posted the solutions online this morning. Everyone should go look at the solutions. Sort of the very least, you should be, even if you didn't get it the first time around, you should make sure you understand what went on and how to solve those problems. Because not knowing it once is one thing, right? Not learning it after that, that's not excusable. So, I think I've said it before. Were I to come in with a quiz that was exactly one of those exam problems, I would have, everyone should get full points on it. So, are there any questions about the test?
I was wondering if you can just go over why it was an inductor instead of a capacitor.
Sure. So for that question, you had a mystery element, a resistor, and a resistor, and both the resistors were 1K. This was 10 volts, and this was a switch that closed at time t equals 0, right? This is your output voltage was across this resistor. And I also showed you that the V out as a function of time looked like this, where this leveled out to 5 volts. You have two questions. Question number one, what goes in the box? Question number two, give me a value for what goes in the box. So, what can we rule out right off the bat? What can it absolutely not be? Cannot be a resistor. Okay? Something is changing with respect to time. That completely rules out a resistor. So if you said resistor, I'm throwing you under the bus. If you said capacitor, we can negotiate. It's wrong, but we can negotiate. So let's talk about why it can't be a capacitor, and then we'll talk about why it has to be an inductor. Okay, because those are both useful conversations to have. So if it was a capacitor, so what do capacitors do? If you put a constant voltage across them, eventually the capacitor will charge. Okay? And remember, the capacitor is I equals C dV dt. So eventually, if you're putting in a constant voltage across this thing, that cap will charge. And when it charges, that means its voltage will reach a constant value. If the voltage is a constant value, what will be the current across that capacitor once it charges? 0. By definition, once a cap charges, if the voltage isn't changing, there's no current. Okay, remember, bless you. Remember, we looked at those. We looked at a parallel plate capacitor, and we said, once it charges, there's no movement of ions. If there's no movement of ions, there's no current. Okay, so eventually this cap will charge. When it charges, there'll be no flow of current. And when there's no flow of current, it's basically just like an open circuit. Okay, so tell me, what's this circuit going to look like? What's my output voltage going to look like if that cap charges and there's no current? 0. If that cap charges and there's no current left in the circuit, then effectively you've got this, right? This is a circuit with no current. So what's your output voltage? It's 0. Okay, is that what we have? No, our plot clearly indicates that as t goes to infinity, we have a non-zero voltage. So that cannot be what the case is here. Okay, that cannot be the case. Yes, sir?
So if you had measured across the capacitor, that would be it, right? If you had asked for DC of t.
If I asked for the voltage across the capacitor, it would have that would have looked like that. Yeah. Right. The voltage across the capacitor, the instant you turn the voltage on, there would have been.
Wouldn't it charge to 10 then?
Oh yeah, it would have charged to 10. Right. Absolutely. Right. That's exactly right. There would have been no voltage, then it would have charged up to 10 volts. And at the same time it charged up to 10, this would have gone, this would have gone down to 0. Good. So now the question is, if it's not a capacitor, and it's not a resistor, and it's not a diode, and it's not a whatever, a million other things we haven't learned about, it's got to be an inductor. So why does an inductor make sense? Inductor makes sense because when an inductor also stores charge, or it stores energy the same way a capacitor, in the same vein that a capacitor does. It stores energy, takes time to charge. But in this case, it stores charge like in an electric field with a current. Okay? So when you store that, initially the inductor is going to look like an open. But once it charges, it looks like a short. And remember, for the inductor, it's V equals L di dt. So in this case, your inductor is going to charge to some value. And when it charges to some value, it's basically going to appear like a short. That's what inductors do, right? When it's charged, it basically just looks like a wire. Now, if this looks like a wire, what's my output voltage going to look like? It's just a voltage divider, right? Once that inductor charges and becomes a short, then all you're left with is a 10-volt input into a voltage divider. And that voltage divider is 1 over 1 plus 1. Right? That's a voltage divider that divides your input by 2. My input is 10. Your output is 5. So that's exactly what's happening. Okay? So in that case, the inductor is charged. And so really so it's an inductor. The only question now is what's the value of the inductor? Well, probably the easiest way to do it would just be to write the equation for this circuit. Okay? And that equation would be that 10 volts minus the inductor voltage minus I times 1K resistor minus I times the 1K resistor equals 0. That's your voltage equation going around the circuit. The voltage around the inductor, the inductor voltage is the same as minus L di dt from that equation minus I times 2K equals 0. So you can reorganize that a little bit to get di dt plus, where am I now? 2K over L I equals 10 over L. So there's your differential equation. How do we interpret a differential equation like that to find the time constant? Remember, first order differential equations are always written, right? So they're always written as first derivative plus variable over tau. So in this case, your time constant has to be L over 2K. Okay, you eyeball the graph. You figure out it takes roughly 5 time constants to charge. So I think the charge time, I think the way I generated it was to say that the charge time was 5 milliseconds. But I think you could have reasonably looked at the graph and guessed anywhere from 4 milliseconds to 7 milliseconds would probably have been an okay range to say charge times. Divide that by 5 to get tau. The only thing left that you don't know is L. Solve for L. I think you should have gotten like 2 henries or something. Yes?
Can we say if we place a capacitor there, we would have a high pass filter and the graph doesn't look like low pass?
You're saying if you put a capacitor here, it would be a high-pass filter. That's correct.
And the graph is low pass.
The graph is clearly a low-pass filter.
So it's a capacitor is not.
Therefore, it can be a capacitor. Absolutely. Yeah, that rationale works perfectly. This is a high-pass filter, right? Sorry, this is a, right, if you draw it like this is a low-pass filter, right? Exactly right. But that's not what's being shown here. Here you're putting in a constant, and the constant is actually getting passed right through. Okay, so that's that low-frequency constant is being passed. So clearly what you have here is a low-pass filter. And we know that's a high-pass filter, so it can't be that. Yeah, I'll buy that logic. What do you think? Okay. Well, that was sort of fun. Questions? No? All right. Well, let's do this. Let's wait till Elliot grades the exams, and then we'll do all the hand-wringing and the negotiating and the, wheeling and dealing. But I actually think, I've sort of instructed Elliot how I want them graded, and hopefully there'll be lots of partial credit. And we'll have a better idea on Monday of how people did. He promises me to grade them over the weekend. All right. I wanted to finish our conversation on low-pass filter equations. Okay, so if memory serves me correctly, we were taking a cosine and putting it into a circuit that looked like this, where this was the resistor, this was the capacitor, this is a frequency. We were assuming that our input was a cosine at some unknown frequency. And I think we did an example where we tried for a particular value of R and C, we calculated what the output voltage would be with respect to various input voltages. Is that right? Good. So I think so if memory serves me correctly, we said something like V out of t equals some magnitude cosine omega t plus some phase. Is that right? So we said if our input is a cosine of frequency omega, our output is also a cosine of frequency omega. The only thing that can vary is the magnitude and the phase. Is that right? I think so. And what was the formula we came up with for the magnitude? Can someone help a guy out here? I'm guessing it was 1 over the square root of
1 plus 4 omega squared.
Can we express that 4 just in terms of R and C? I mean, it was 4. I think that's right. But like, if we just wanted to leave it in terms of the resistor and the capacitor values, do we do that? Yeah. Okay. Omega RC squared. Yeah, absolutely. So if you happen to know the value of R and C, you plug it in there. Okay? All right, and what about the phase angle? Do we get a formula for the phase angle?
Minus inverse tangent.
Minus inverse tangent.
Omega RC over, yeah, just omega.
Just omega RC. Beautiful. Okay? Now, I claim that everything you need to interpret this as a low, we agreed this is a low pass filter, right? We've talked about it like 17 times now, I think. So let's look at, let's start for a minute by looking at K. I think when we actually did the answer out by hand in class, we had this observation that when omega was small, my output was pretty high, right? So, and then when omega was big, my cosines were getting really, really small. And that matched my rationale that this is a low-pass filter. So let's try this for a second. When omega is really small, so engineers do this all the time, right? I mean, any high school kid could take that number and plug it into a graphing calculator and look at the result, right? But we got to step up a little bit, right? Engineers need to be able to look at this and have a little intuition behind this. So what I want to do is I want to look at two cases. What happens when omega is really small, at really low frequencies, and what happens when omega is really big? And we'll make some simplifying assumptions along the way. So I want you to look at my amplitude. We're going to forget about phase for a second. Let's just look at the amplitude plot, the amplitude portion of this. Because this is really what's going to tell me whether the cosine that I put in is going to be passed or rejected. So let's say that omega is really, really small, low frequencies. Okay? So when omega is small, that's what I mean by low frequencies. So when omega is small, what's going to happen to K? It's going to be pretty close to 1. So engineers play this game all the time where you look at this denominator and you say, okay, there's two terms in this denominator. There's the 1 and the omega RC squared. So I want to think about which one of them is going to win, like they're having a fight. So let's say omega is really, really small. Okay? I haven't really defined what really small means, but let's just say that there is such a thing as really small. So who would win in a fight if omega was really small? Which term would be bigger? 1. Okay. We can all agree that if omega is really small, then even though this term is really still here, we can say, you know, it's probably so tiny with respect to 1. Like, what if it was 1 plus 0.001? Screw the 0.001. Let's just like ignore that and round it off or whatever. So if omega is really small, you're left with 1 over the square root of 1. And in that case, your magnitude is roughly equal to 1. What about for large frequencies? All right, what about for omega is really large? Right? What about for high frequencies? So what happens to my k when omega is really big? Right. What term is going to dominate in the denominator when omega is really big? The omega RC squared term, right? So let's say omega is a bazillion. Okay, a bazillion squared plus 1. Forget the 1, right? The 1's just a, you know, it's insignificant. So if omega is really big, you've got omega RC squared, square root. So those cancel. So now you're just left with 1 over omega RC. And if omega is really, really big, what is 1 over omega RC going to be? Really, really small. Okay? So we'll say that k, in this case, will be approximately 0, or really small. Okay, let's do the phase angles while we're at it. If omega is really small, what's my phase angle going to be? What's inverse tangent of almost 0? Does everybody remember how our tangents work? I need some scratch paper. There's tangent. So if omega is really small, then I'm taking inverse tangent of almost 0. So what angle has its tangent is 0? 0. Now in this case, your phase angle will be pretty close to 0. What about when omega is really big? What will your phase angle be? When omega is really big, like when omega approaches infinity, you're taking the inverse tangent of infinity, or an inverse tangent of a really big number. Okay, how do you take, so looking at my graph here, what happens when I take the inverse tangent of a really big number? Right, here's a really big number. If I take its inverse tangent, I get pi over 2. And the equation reminds me I need to stick a minus in front of it. So minus pi over 2. So let's put the pieces together. When I put in a low frequency cosine, my output is going to be basically it's going to be 1 cosine omega t plus 0. Which is pretty cool because my input voltage was also 1 cosine omega t plus 0. So at low frequencies, what's the relationship between my output and my input? They're the same. You see how these are the same? So for low frequencies, output equals input. Does that sound like a low-pass filter to you? Cha-ching, low-pass filter. Because low frequencies are passed. Now, for the same input, what's my output at high frequencies? It's going to be 0 cosine of omega t minus pi over 2, which is basically, it means 0 times anything is basically 0. So I put in a cosine. If that cosine's got a low frequency, it's going to come unscathed. It's going to come right out of this filter. If you put it in a high frequency, it's getting the boot. It's going to come out as 0. Yes, sir?
Which ones are your zeros and which ones are your thetas?
Huh? Oh, yeah. Okay. Theta? 0. Sorry. That's a 0. That's a 0. That's a 0. Sorry. That's a theta. No. Ooh. That's a 0. 0. Theta. Bad, professor. Okay. I'll try a little harder next time to clean that up. Okay. But you get the idea. Low frequency cosines get passed. High frequency cosines get rejected. Ones in the middle, I mean, we've done the extreme cases. The ones in the middle, like a little bit passed, a little bit rejected. Okay, a little bit of both. What do you think? Okay, so here's what I want to do. Let's actually go and make a plot and kind of analyze a little bit how this looks. So let me go ahead and get the thing set up. Do you want Excel or do you want MATLAB? MATLAB? Do you have, what is your level of comfort with MATLAB? Okay, well that was resounding. Let's use Excel.
That top one, isn't that a theta? Your Vn?
Where?
Below frequency.
Vn equals 1 cosine omega t plus, oh dang. Oh no, it's 0 because you're inputting it with 0 phase shift. Yeah. Okay. Somebody mind? I'll get it. No, let me. You guys look so comfortable. Okay, no sleeping. Or at least no snoring. How about that? You ever been in a lecture and somebody snored so loudly that everyone else could hear it? That's always fun. Let's see here. We are not looking at the same screen. Nope, that's not it. Source. All right. You guys want to see what you'll be doing next semester? You'll be doing a little bit of, survey says, it's coming, I think it's coming. There it is. There we go. That's what you'll be doing next semester. All right. So let's go ahead and pull up Excel. Okay. So, all right. So let's pick values for R and C. What should we make for our filter? I don't care. Help me out. Let's call out a resistor value. 1K. Call out a capacitor value.
200 microfarads. 1 micro.
I got 200 microfarads. Okay. So, now let's have a list of frequencies. So we'll have omega, and then based on omega, we're going to calculate the magnitude, and we're going to calculate the phase. And then we're going to make a plot. One plot will be frequency versus magnitude, and the other plot will be frequency versus phase. And we're going to get real comfortable making these plots. Okay, part of the problem is I don't really know what corresponds to a low frequency, and I don't know what corresponds to a high frequency. I'm going to go ahead and just hard code in a couple values, and we'll see what happens. So let's try 1, 2, 5, 10, 20, 50, 100, 200, 500, 1,000, 2,000, 5,000, 10,000, 20,000, 50,000. So I'm basically putting in a whole bunch of frequencies here. Is that enough zeros? Oh, I think I missed one. Hold on. 1, 2, 5, 1, 2. And that was what, 1 million? Okay, so let's see how that works. So I'm basically trying a whole bunch of frequencies. I'm going to start all the way with 1 radians per second, and I'm going to go all the way up to 20 million radians per second. Okay? All right, and I'm going to employ, let's see, what am I going to do here? Okay, so let's try this. So what is my formula for K? It is equals 1 over the square root of 1 plus, and then it's omega RC, the quantity squared. So all I got to do is I got to say What's my omega? It's that value times R times C. Oops. Omega times R times C squared, and I close it. All right. And let's plot that. Let's just make sure it gives me. I want my answer in a decimal. Okay, so there's a low frequency. Is it being passed? Totally, right? Put in a frequency of 1 radians per second. It's coming out almost exactly as it went in. That's good. So part of the joy of Excel now is that I should be able to get all these other frequencies by just doing cut and paste, right? Yeah, basically fill down, but it just will do it automatically, except it's actually going to give me a problem. Uh-oh.
You're using that one frequency for every.
No, it should. So what it should do, so for those of you who don't understand, are not familiar with how Excel works, if I take this formula and I copy it and I paste it, then what it's supposed to do is it's supposed to be smart enough to know that if in row E2, I was, in calculating E2, if I was referring to D2, that it knows that when I advance to row E3, I should increment to be, instead of analyzing D2, it'll be analyzing D3. And let's see if it did that. It did, okay? See how in analyzing my omega, it automatically says, hey, you don't analyze D2. When you're doing this row, analyze D3.
What the gender be?
The problem is it also advanced the cells where I was storing my resistor and capacitor value. Okay, so there's a little Excel trick. I don't know if anyone knows this. If I put a $ in front of the B1 and B2, it'll always use the same one. So now when I come down here, it incremented D3, so I'm using this frequency, but it's still using cell B1 and cell B2, which is where my resistor and capacitor values are. So it won't change those. So copy, paste. Okay, what do we got? Do I have a low-pass filter? Uh-huh. I think we do. You feel good about that? Let's go ahead and make a plot. So all I'm going to do, I'm going to highlight those two cells. I'm going to say, give me a chart. And here's my chart for K. Holy mackerel, what has gone wrong? So let me just reiterate what I did. I just said, please create a plot of all the values in column E versus all the x values in column D. Believe it or not, this plot is correct. The scale is crazy, right? I mean, I'm going all the way out to 20 million, right? So my x-axis goes from 0 to 20 million. Where does all the stuff actually happen? Where does all the interesting stuff happen? Starting at 1 radians per second, going all the way to, like, at best, all the drama's over by like 20, maybe 1,000 hertz, 1,000 radians per second. So all the stuff that we want to see is actually mushed into this tiny little sliver in the beginning. So how can I fix that? How can I make my plot so I can actually interpret it a little better? Easiest solution. Well, let's just zoom in on the x-axis. Okay, so I can actually double-click on my x-axis, and instead of going all the way out to 25 million, how about we just go out to 2,000? What do you think? It's better. I mean, at least I can see something now, right? So yeah, this is exactly what a low-pass filter is going to look like. Bless you. Let me do a little something real quick. I'm going to add a few more frequencies. Oh dear, don't worry about that. Let's see. So let me do 0.5, 0.2, 0.1, 0.05, 0.02, 0.01. Am I doing it right? Did I lose a step? No. 0.005, 0.002, 0.001. Okay, I just want to get a few more points in there. Okay. All right, so that's what a low-pass filter looks like. And you know, we could do this process of zooming in a little more, but I think you can agree with me that the way I'm doing this does leave a little bit to be desired, because it seems like no matter how I try to zoom in on the plot, I can either get a nice look at the low frequencies and no look at the high frequencies, or vice versa. It's very hard for me to capture the details of what's going on at the low frequencies and the details of what's going on the high frequencies at the same time. Okay, just because the scales are so different, right? If I want to see what's going on between 0 and 2 radians per second, my plot has to ignore what's going on up at the millions of radians per second. So this is a standard problem, and for that reason, no one ever creates these plots like this. The standard solution is, instead of using a linear x-axis, you use a logarithmic x-axis. So does everybody use like the log graph paper, like in pre-calc, wherever they teach you that nonsense, like how to count the divisions on log graph paper? That's exactly what we're going to do here. The nice thing is that in Excel, all I got to do is come and click this button here that says logarithmic scale, and that will automatically convert my x-axis into a logarithmic axis. All right, and now I can actually go back out to my maximum value of, let's see, what is my maximum value? What was it? 20. Oh, I see. If I just leave it clicked at maximum, it'll automatically give me the maximum value. Now, how do you feel about this? It still only went to 1,000. Yeah, it still only went to 1,000. I don't know how I feel about that. It did lie to me. What's up with, because I told it to only, hold on. Let me just regenerate the graph. I think I know what happened. Because originally when I told it to do the graph, I only told it to do a few, those rows, and then I added more numbers. It's still only plotting for me those first few numbers. So I'm just going to recreate the graph with the entire column. And once again, I have to just tell it to give me the log axis. Oops. Scale. Yeah, thank you. Oops. Ah! Come on, Obaid. There he is. I'm back. Okay. So by converting my x-axis to logarithmic spacing, now I can see everything. Okay? Now I've got a lot better picture of what's going on. So you can see when you have, just as a reminder, let me put the grid on this. As a reminder, when you do logarithmic spacing, you have to speak to get a grid around here. Let's see. What if I right-click on here? Oh, well, there's some way to get a grid. Add major grid lines. Okay, so as a reminder, when you do logarithmic spacing, then, like when you have regular spacing, you go 0, 1, 2, 3. So going between grid lines adds a constant amount. When you have log spacing, going between grid lines multiplies by a constant amount. So this is 0.001, this is 0.01. That's multiplying by 10. Multiplied by 10, 10, 10. So every grid line multiplies your frequency by a factor of 10. And that's how you're able to compress all the frequencies onto one plot, all the way down from 0.001 radians per second all the way up to 20 million. Okay, so that's nice. So that's the first standard thing that we do. The second standard thing that we're going to do is, instead of plotting our y-axis, so right now we've got our input is 1. So at the lowest frequencies, our output is a cosine of 1. And it goes all the way down to 0. So this means that output equals input, and this means that output equals 0. So the other thing that we do that's a little bit different when we make these plots, although what you're looking at is perfectly fine, there's one more trick that we do. And that is, instead of plotting k, as a raw value. We're going to convert it one more time into something called decibels. Okay, and decibels is just a different unit of magnitude, but it's a logarithmic unit. So let me go ahead and do that calculation, and then I'll tell you where that came from. So dB, all you got to do for dB is you take 20 times log, now I've got to be careful here, 20 times log base 10 of your gain. And that did not work at all. Why did that not work out? Oh, no, it did work out. Okay, I'm back. Hold on. Let me just convert that into, where'd my, sorry, I just got, oh, there it is. Ah! Sorry. I got lost for a second. Good. So when you take a log base 10, a gain of 1, right? Output equals input, and that's a gain of 1. That corresponds to 0 dB. 0 dB is like 0 change. There's no change between output and input, 0 dB. So I'm going to copy and I'm going to paste that down.
What was that formula again?
20 times log base 10 of your magnitude. You have to be careful. In both Excel and MATLAB, if you just say log, usually it gives you the natural log. You have to say log 10 in Excel in order for it to give you log base 10. So if you see my formula, 20 times log 10, all of that word, log 10, is a function in Excel. Log base 10 of your gain. Okay? So now I'm going to recreate my plot one more time, but instead of plotting frequency versus my magnitude, I'm going to plot frequency versus the decibels of my magnitude. So give me a chart. And let's, again, go back to logarithmic values. Okay, and finally we're at, something we are, I'm comfortable, like this is sort of what an engineer would look like. And you're going to see tons of these. Now, this is a low-pass filter. Okay? Low frequencies are being passed with a gain of 0 decibels. High frequencies are being rejected all the way down to 100 decibels, 100, 200 decibels, whatever. Okay? One of the nice reasons why we plot this, you see how this became a line? That's actually going to wind up being valuable to us later on down the line. Maybe not even in this class, maybe once you get to signals. But before, when I was just plotting it versus K, it just kind of ducked down. It went down to 0. Here, instead of going down to 0, it will just always continue as a line. And that's going to wind up being useful to us to be able to visualize the data like that. But still, any way you slice it, you look at this, what we've got is a low-pass filter. Okay? So all I've done is I've taken that formula that we calculated for K, which we got using our phasor notation, and I'm plotting it now in Excel, and Excel is showing me proof positive that I have a low-pass filter. Low frequencies are being passed, and I can tell they're being passed because the magnitude of the output is 0 dB. Okay, that's a gain of 1. And high frequencies are getting rejected. Questions?
How do you determine frequency where it changes?
I'm getting there. I'll get there. Yes? Do you have a question? No, you have a question.
Are you gonna? Would you be willing to post this on Blackboard?
Yes, absolutely. I'll put this code on Blackboard. Okay, so now let's answer the question. How do we know? So how do we know the cutoff frequency? Yes.
Sorry, can you repeat what you said about low frequencies being passed because?
Oh, did I erase that? Okay. Let me just write it over here. So we agreed that when frequency is small, K equals 1, okay, implying that the magnitude of the output cosine is the same as the magnitude of the input cosine. And if you take K and convert it into decibels, you've got 20 log of 1. Log of 1 is 0, so that gives you 0 dB. So the way you read this plot is you look and you say, okay, well, my y-axis is in decibels. At low frequencies, my magnitude is 0 dB. 0 decibels, that means that I know that means k equals 1. Okay, there's no 0 dB means there's zero difference between input and output. At high frequencies, we learned that k was very, very small, right? Almost 0. So what happens if you take a number that's almost 0 and convert it into decibels? Like if I take 0.001, that's a pretty small number, and convert it into decibels, right? So that's saying 20 log base 10 of 0.001. So how can I let's just sort of walk through this hand calculation just so we can have a feeling about how decibels work. So what is log base 10 of this arbitrary small number that I've picked out? Does everybody remember what question log answers? When we say log base 10 of 0.001, really what we're saying is 10 raised to what power equals 0.001. That's what logarithm does. It answers that question. What goes up here? Negative 3. 10 to the negative 3 equals that number. So negative 3 times 20 is negative 60. Okay? What if I made it even smaller? What if I made it 0.0001? Negative 4. That would give you negative 80. What if I put another 0 in here? Negative 5, negative 6, negative 7, and so on. So your decibels would keep getting more and more negative. But it can never get all the way to, you can never take log of 0 because our k can never reach 0 unless k reaches infinity, unless omega reaches infinity. So we're never going to get a 0 here. We're only going to get smaller and smaller numbers. And as this gets smaller and smaller, your dB gets more and more negative. So when your dBs are close to 0, that's good. That means output equals input. When dBs are very negative, that indicates to you that your output is getting smaller and smaller and smaller. You can have positive dBs. That corresponds to a gain, where your output is actually bigger than your input. Okay? But we can talk about that. You know, for example, if you have a op-amp circuit that amplifies your signal, then you have positive dBs for gain. What do you think? We feeling each other? Okay, so now let's talk about what happens. Let's talk about how we know where the cutoff frequency is. So let me do this. I'm going to change. Let me do one thing. I'm going to just change it so I don't want it to keep changing my frequency axis anymore. I just want it to hold everything constant for a second. Okay. So I'm going to change my. You can't see the. Okay. Okay, now you can see that. So I'm going to change my resistor. So I've got it at 1,000. I'm going to make it 2,000. Okay, ready? Keep your eye on the plot. Hold on, that didn't do any good. Let me. I want to change my. I just want to modify my plot, so I don't want it to rescale the axes every time I change something. So I'm going to, there we go, just keep it all there. All right, so let's try that again. So I'm going to take my resistor and I'm going to double the resistor value. What happened to the cutoff frequency? Okay, I'm going to double it again. I'm going to go to 4,000. I'm going to go to 8,000. What's happening as I increase R? Let's do 20,000. So I want you to think about two things that are happening here. I want you to think about, is the slope of the line changing? I agree. I don't think the slope of the line is changing.
Cutoff frequency.
But the cutoff frequency is getting smaller. So I'm introducing a new phrase here. The cutoff frequency is the frequency that we say below the frequency is where it's being passed, and above the frequency is being rejected. And I'm not, we haven't defined how I calculated that, but clearly we can see that the pass band, those frequencies that are being passed, the pass band is getting smaller as I increase my resistor. Okay, let me go back to my original value of 1,000. Okay, now I'm going to make it big. I'm going to make my resistor bigger, smaller. So if I make it 500, 200, 100, 10, 2. Okay, you see what's happening? So clearly, not only is it possible to make a low-pass filter, but it is also possible to design a low-pass filter where you select which frequencies are passed and which frequencies are rejected. Right? Because, what if you want to pass, like if you're doing an audio signal, you might want to pass frequencies up to 22,000, up to 20,000 hertz, because that's where audio signals kind of operate up to. But if you're doing some other application, you might want to set your pass bands somewhere very different. So now it seems that there's some relationship between the value of the resistor and the cutoff frequency. All right. What about the capacitor? Let me put this back to 1,000. So what do you think is going to happen if I change my capacitor value? So right now my capacitor is at 200 microfarads. What do you think if I change it to 100 microfarads? Is it going to change at all? You have three choices. I'm going to have the value I'm going to double the value of C. I'm going to double the value of C. Is my cutoff frequency going to get higher, lower, or stay the same? And you don't really have any, I can't really expect you to know the right answer, but I want you to at least sweat it out and think about it for a second. If I have the value of that capacitor, double. I'm going to double the capacitor. That's what I said. If I double the capacitor, what's happening to my cutoff?
Small.
Right. Think about it mathematically for a second. Think about it mathematically for a second. Your formula for K is 1 over the square root of 1 plus omega RC squared. We've already established that if I take R and increase it, my cutoff frequency gets smaller. Now look at this formula. If I double R, or if I double C, does it make any difference to the equation? No. Right? R and C are tied to each other. So doubling the capacitor should have exactly the same effect as doubling the resistor, because they're sitting right next to each other in the equation, right? So a moment ago, I doubled the resistor. Now I'm going to double the capacitor. So instead of going for 200 micro, I'm going to try 400 micro. And sure enough, my cutoff frequency got smaller in exactly the same way that it happened when I doubled my resistor. And if I go to 800 micro, and if I go to 1600 micro, oops, E6 minus. Oh dear. Oh, you actually care about that? All right, so on and so forth. So it seems that if you increase your resistor or if you increase your capacitor, you lower your cutoff frequency. Conversely, if you lower your capacitor or you lower your resistor, you increase the cutoff frequency. On Monday, we will learn how you can actually, instead of going by trial and error, if I come to you and I say, build me a filter with a cutoff frequency at this many hertz, how you could actually pick the resistor and the capacitor value in order to get exactly the cutoff frequency that you want. Okay? But I think at the very least we can agree that it is your choice of resistor and capacitor value that sets your cutoff frequency. Pretty intense, huh? So all of a sudden you've learned something pretty useful in this class. I'm going to post this to Blackboard right now. So I advise you to play around with it a little bit over the weekend. And let me know what you think.